By introducing myself. So, my name is Rohit Kumar Singh, and I am doing PhD from IIT Madras. It's my fifth and final year of PhD, and I work in the area of experimental high energy physics. So, completely different from this topic, which is statistical mechanics. But we do use some concepts of statistical mechanics during the data analysis of uh, the experimental data that we get from CERN. So yeah, so if you want to ask something about my PhD, you can feel free to ask. And and so this is the second live session. So last week there was some confusion about the timing, and I wasn't able to uh, conduct this session. But yeah, now it will be regular on Saturday 6 to 8 p.m. So this course is being taught by Professor Dipanjan Chakrabarti on NPTEL. I hope, I believe you guys are following the course on NPTEL, basically the lectures. And so here I'll try to just recap some of the concepts that are being taught there, and try to solve some example problems to make it easier for you to, solve the tutorial assignments for the for all the weeks. So yeah, I think that is all from my side. So if you have any question, you can ask. Otherwise, I'll start some discussion. So okay, I think everyone is fine. So let's recap some of the concepts. So okay, so all of you are familiar with laws of thermodynamics, right? The first law, which is basically deals with the conservation of energy, and the second law, sorry, yeah, first law, which is just the conservation of energy. Second law introduces us to entropy. So this thing dq, and combinedly we can write them in this form. So if you have a hydrostatic system, so we can write the work done like this. But this can change for different kind of system. But for hydrostatic system, so this is what we have for the work, for the, combined first and second law can be written like this. So basically, yeah, anyone has any question? Someone raised their hand. I think it was mistake. Okay. Yeah, if you have any question, you can unmute and ask at any time. Okay. So, okay. Yeah. Now, so these are first and second law of thermodynamics, but just so that we are all on the same page, I will again go to some basics. So we know that there are thermodynamic state can be defined by macro state, okay, and the macro state variables can be classified as extensive and intensive quantity. We know that, right? So for example, for a hydrostatic system, volume, number of particles, uh, these are, extensive quantities. Chaitanya, do you have a question? You can ask. You are raising your hand. I don't know. If you don't have any question, please don't use the hand button. And other quantities like pressure, temperature, these are, intensive quantities. So what is the difference between them? So, so basically, extensive quantities are, additive in nature. So if your system gets bigger, these quantities get bigger. Okay, and mathematically we write them as like if you have lambda number of subsystems with a thermodynamic state given by suppose SV, and so S is the entropy, uh, okay, which is also an extensive quantity. So this is also an extensive quantity. So basically lambda subsystems with the same macro state, if you add them up, it will have the macro state given by this, sorry, lambda v and then lambda n, sorry. Okay, so everything has added up, and then we know that we have relation with internal energy. So internal energy can be written as a function of entropy, volume, and number of particles, and so on. Okay, and so for the whole system, it will be lambda S, lambda V, lambda N, right? And since internal energy is also a extensive variable, so it will be lambda times the internal energy of one of the subsystem. Okay, and this equation is a very special equation in mathematics, which implies that U is a homogeneous function. Okay, so the internal energy is an homogeneous function, and there is a general relation for homogeneous functions. So if there is a function given as which has these sorry, anyone has any question?
Someone? What is the
Yeah.
homogeneous function?
Yeah, can you speak up?
So the homogeneous function.
Yeah. I couldn't hear you well. Can you try to speak loudly or closer to the mic? Or you can write in the chat maybe. You're asking something about the homogeneous function, right?
Yes, sir.
What is it?
Why is the homogeneous function?
I could not hear you. Can you write in the chat? So I'm saying if there is a function, if there is a homogeneous function, general function like this, which has xn, dependent variables, and this can be, if this can be written like this. Okay, where where lambda is arbitrary. So why this function is used here? Okay, so no, I just wanted to point out that internal energy is a homogeneous function, so there is a consequence of it. Okay, so that's where I'm going at. So if any function is a homogeneous function, okay, uh, written like this for arbitrary lambda, okay, and so since lambda is arbitrary, so this is a mathematical, mathematical uh, truth. Okay, so we can choose lambda is equal to 1, and something called Euler identity. uh, if you have any question, please ask. Okay, and for these kind of homogeneous function, Euler identity given by this, so kf, this holds true. Okay, now since our internal energy is a homogeneous function, uh, uh, because we have this thing, and here k is 1, right? Because it's just lambda u, so k is 1 in this case, and so we can write simply u, using this relation, this Euler relation, we can write u. So the dependent variables are s, v, and n. Okay, so s du by ds, okay, plus, so these are partial derivatives, because here v and n are constant. Okay, then v del u by del v, here s and n are constant, and then n del u by del n. Okay, here other two are constant. Okay, so we can write something like this. Now if you notice from this first law of thermodynamics, first and second law of thermodynamics, what we have here is, so temperature is simply del u by del s at constant volume and n, right? Everything fine with this? Everyone fine with this? This is evident from here, right? If you take partial derivative of internal energy as, with respect to entropy, keeping the volume and number of particles constant, it equates to temperature from here. Everyone is fine with this, right? Also, one more thing is there is, if you take partial derivative with respect to volume, keeping the entropy and number of particles constant, this equates to minus P, negative of pressure. Okay, and similarly you have one more so let me keep right. So you have one more thing here, is that partial derivative of chemical potential with respect to number of particles. This is partial derivative of internal energy. Yeah, del u by del n at constant s and v will give you chemical potential mu. And if you put these three things here, what you get is a very beautiful relation like this. Okay, and this you can use in solving problems. So what it so we now if you look at it together, we were able to write the internal energy just in terms of temperature, entropy, pressure, volume, and number of particles. Okay, because because the homogeneity, because this is a homogeneous function. Okay, otherwise this would have not been possible. Okay, so like give it some thought. It's a very interesting thing. Now yeah, now what you can do is you can try, you can now try to vary it, I mean differentially. So just uh, I mean just differentiate this equation. So we are making finite changes in all of these quantities. So you get this, and then okay, and you will notice that, so this 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 and this are from the first law of thermodynamics. Okay, so because we have du minus plus edv minus mu dn, right? And so these all cancels out, and what we remain with is this one, which is called Gibbs-Duhem relation. So so this is kind of a complementary to the first law of thermodynamics. So what first law of thermodynamics tells us is that you cannot arbitrarily vary the extensive variables like volume and number of particles and entropy. Okay, they should be constrained, and they are constrained by this first law of thermodynamics. And similarly, what Gibbs-Duhem relation tells you is that you cannot arbitrarily vary the uh, intensive quantities like temperature, pressure, and uh, chemical potential. They should be constrained, and they are constrained through this relation. Okay, so in a thermodynamic system, if one of the thing varies, then other one, I mean it will affect another. Like if one of the extensive quantities changes, it will affect other extensive quantities, and if one of the intensive quantity changes, it will affect other intensive quantity. So this is what these two equations, the first law of thermodynamics and the Gibbs-Duhem relations, tells you. Okay, so although these things are discussed in lectures in detail, but I just wanted to repeat this. And the calculation that we are doing, they will help us in solving the problems also. And similar thing you can do with entropy also. So we know that entropy is a function of internal energy, volume, and number of particles. And similarly you can show that this is also a homogeneous function, and you can calculate, I mean you can use the Euler relation in this case also, and finally you will get something like this. So I mean doing the same algebra, you will get something like this, which is equivalent, which is just same as this relation that we got earlier. So this you can try doing. Okay, and you can also then having the finite variation, you can also calculate the Gibbs-Duhem relation in entropic form, and you will get something like this. I'll just write it out. Okay, which is also equivalent to this. Okay. Okay, so yeah, this is fine. Now I'll just write out some identities that identities and formula that will help us later in the course to solve problems basically. So just so that you remember it. So for a function fxyz is equal to 0, so if we have some a relation like this, there is a cyclic identity that holds given by given like this. So okay, so this is called the cyclic identity. The derivation has been done in the lectures, you can go and check it. Okay, now from here you can derive something interesting. So if you hold the z constant, so that means dz equal to 0. uh, yeah. So yeah, then what will happen is that you have basically fxy is equal to 0, right? And then you can write this, I mean the cyclic identity becomes something like this. And so you can write something like this. So yeah, you can also use this thing in problems. Then then there are something called response functions. I don't know if you have learned about it. So so what response function does is, if you have a thermodynamic system and you perturb it in some way, uh, you will, I mean you can measure the change in the system through these response functions. So for example, there is something called compressibility, so which is relative change in volume with respect to pressure that you have applied on the system at constant temperature. Okay, so because the temperature is constant, so it is called isothermal compressibility. Okay, and this is given by kT. And then there is something called beta T, which is relative change in volume as function of temperature, with respect to temperature at constant pressure. Okay, and so think about it. So this is just the change in volume at with respect to temperature. So you are giving heat to the system, you're raising its temperature, and the volume is changing. So it is just expansion. So this is called expansion coefficient. Okay, and these are two response function. And if you just take the ratio, I mean divide these two, you get this relation between the uh, expansion between these two response function basically. Okay, so this is also one useful relation. Okay, so yeah, what else? And then if you have a a hydrostatic system where pressure is given as a function of temperature and volume, the finite change in pressure can be written like this. And in terms of these two response functions, you can write them like this. And so these are experimentally measurable quantity. Okay, so you can measure them experimentally. Okay, so some for some finite change of temperature and volume, what will be the finite change in pressure? uh, if you have these two response functions, then you can calculate this thing. Okay, and yeah, I think that's I mean that is all that I wanted to recap for now. If anything else comes up during the problem solving, I will try to explain that. uh, yeah, I think this will be fine for us. So let's go to let's I mean try to solve some problems. So I'll expect that you guys will interact with me while solving the problems. And please correct me if I do something wrong. Okay, so let's start with our first problem. Okay, so now just now we have discussed this thing. Okay, so suppose you are given a thermodynamic system which obeys the fundamental relation between the entropy, the internal energy, volume, and the particle number n as this. So this is just the fundamental relation of first kind. Uh, Entropy as a function of internal energy, volume, and number of particles. Okay. And the question asks is what is the internal energy as a function of temperature, number of particles, and volume. So from here we have to find the relation, fundamental relation for internal energy. Okay, so anyone has any idea how to uh, go about solving this problem? Anyone? Guys, are you listening? So what can we use? Like I wrote bunch of relations earlier, right? So I wrote the first law of thermodynamics. I wrote out the you know Gibbs Duhem relation. So what do you think I can use to solve this kind of problem? Anyone suggest?
Sir, maybe the first law of thermodynamics. 1 by T equal
Okay.
to
So how? Yeah. So
like del S by del U.
del
With
S.
constant of volume and and
So you're saying okay? Let me just first write the first law of thermodynamics. So we have okay. Now what you're saying?
sir, we can use the law of thermodynamics like you taught us like 1 by T equal to del S by del U with constant of V and N.
Yeah. I wrote that thing, right? Just here I wrote that thing here, right?
Yes, sir, yes.
Yeah. So yeah, you're right. So we can use del S by del U, keeping volume and number constant. It will give me 1 by T, right? This is just from the first law of thermodynamics. And so S is given, and just we have to differentiate it with respect to U. Okay, so del S by del U, so A is constant, so yeah, 1 by 3 will be multiplied, so A by 3, and then so yeah, we are keeping V and N as constant. Okay, so we don't need to worry about them. So this whole thing 1 by 3 minus 1, and then multiplied by the constant Vn, right? Please let me know if I make some mistakes. So UVn 1 by 3 minus 1, it's minus 2 by 3 Vn, right? And so 1 by T, so I'm putting just del S by del U as 1 by T, keeping in mind that the volume and N are constant. So it will be AVN by 3 here, UVN. So I'm taking that in denominator, okay, and then the volume and N cancels, I mean you can cancel the powers. So okay, let me do that. So V will be 1 by 3 power, and 1 by 3, and then 3U 2 by 3, and we want to calculate the internal energy, right? So U 2 by 3 is equal to AV 1 by 3 and 1 by 3 T by 3. And so internal energy is simply T by 3, the T by 3 by 2, because we are removing the powers from U and giving it to the other side. Exchange of powers, like in democracy. And finally we get this answer, okay, which is the second answer. Okay, so this is just a simple problem. So so see the power of first law of thermodynamics, and obviously the consequence of second law, that we had the relation of entropy. Okay, I mean we were given the entropy of a thermodynamic system, and now we are able to write out the internal energy of the system. So I mean, so but what is the, what is the relation? Do you know the physical sense of relation between entropy and internal energy? How they are related? I mean, how do we understand them? The relation between them from second law of thermodynamics maybe. Uh, do anyone know what is the direct relation between entropy and internal energy? There is a beautiful statement. Anyone? So I'll give you,
Sir,
yeah.
can we say that with the increase in internal energy, the entropy of a system increases?
I mean, not necessarily, not always, but you are getting there. So yeah. So suppose you have a system which is kept isolated, so there is no heat exchange. Okay, there is no work done on the system or anything, but uh, but if the system undergoes some spontaneous change, like if it suddenly expands, so you have a compressed gas somewhere and it suddenly expand, then what will happen is that the entropy uh, will try to maximize itself. Okay, this relation, right? And so it will go under, the system will go under a change where entropy will maximize and the internal energy will be minimized. Okay, the system will go to such a equilibrium, and this is what we call equilibrium. So in attaining equilibrium, it will try to maximize the entropy and minimize the internal energy. Okay, and since both are also what we call this uh, mm, state function, right? So they don't depend on the path taken for the change of the system. They just uh, depend on the state of the system, the thermodynamic state of the system. So yeah, this is the relation between them. So okay, so let's go to the next problem. So for the same, this is a sub problem of the above. Okay, so for the same entropy and internal energy that we found out, uh, we want to calculate the thermodynamic equation of state. So thermodynamic equation of state means the relation between the pressure, temperature and volume, right? How do we do that? Again, anyone? What can we use here? You have entropy as function of internal energy, volume and n, and you have uh, internal energy as a function of temperature, volume and number of particles, right? From these two, can you write out the equation of state, thermodynamic equation of state of the system? Relation between pressure, temperature and volume. How can you do that? Yeah, anyone?
Sir, please repeat the question.
Okay, so you have given the relation of relation. So I mean, this is just a continuation of this problem. Okay, so for the same problem, you have to find the thermodynamic equation of state. You have this. You have been given the entropy SU as a function of internal energy, volume and number of particles. This is what is given in the problem, right? And then we calculated the internal energy in the last problem, which was this thing. So I'm asking, given these two, can you calculate pressure as a function of temperature and volume? Does anyone have any idea? let me write out again. I mean, to give you a hint, let me write out again the first law of thermodynamics. Now, so you have, temperature here, pressure here, and the change in volume here. So everything is there. Also, you have change in internal energy here, change in entropy is here. So everything is here. So how can you use this to derive this thermodynamic equation of state? So if you come across this kind of problem, first you try to write out what information you have from this first law of thermodynamics. So again, I am writing it out. So you can find out temperature at constant volume and number of particles. Then you have negative of pressure, constant entropy and number of particles, and lastly you have chemical potential, entropy, fixed entropy and volume, right? So what if you divide this and this? We can do that, right? So what you will get is,
Sir, sir,
yeah,
the formula goes like T into del S by del V minus del U by del V is equals to P.
sorry,
I think the formula goes like T into del S by del V minus del U by del V is equals to P. So by calculating that, we can get the value of P.
yeah, P, what you're saying, P is equal to,
Sir, I was telling P is equals to T into del S by del V minus del U by del V. So by calculating this, I think we can get the value of P
but
here.
where did you got this formula? From here, from first law of thermodynamics?
From whatever written on the screen, sir.
Yeah. So you're saying T is equal to del U by del S?
P is equals to T into del S by del V minus del U by del V.
Yeah, wait. I see where are you getting. So you just divided everything by del V, right?
Yes, sir.
But you don't have this thing, right? I mean, I understand we have entropy, entropy as a function of volume, internal energy as a function of volume, but how do you calculate this? So that's why you can just divide this and this, right? And that will give you, that will cancel out the internal energy, and you will just get this at fixed internal energy and number of particles, right? And then since you have the entropy as function of volume, you can just calculate it. You can calculate this derivative. So it will be similarly will be like this, and then you can substitute it here, and doing some little bit of algebra, you will find the answer. So let me know if you want me to solve this properly. It's just algebra. You just put it here and just solve this equation and you'll get this. So this is the equation of state. So here, what I have used, did anyone notice? So here I have used this relation basically, okay, to calculate this using these two.
There's a minus p.
Yeah, because there is the negative here, right? In this cyclic identity, you have minus 1 here, so that compensate this negative sign. So just try to work it out. You will get it. Okay, so any more question here? Okay, if not, then let's go to the next problem. So for the same system, what is the specific heat at constant volume? So specific heat at constant volume. So specific heat we know is the change in internal energy with respect to temperature. Okay, if the temperature of a system rises, how does the internal energy changes? And since it is at constant volume, so this, and also particle number is fixed. And since we have the relation of u as function of T, V, N, so this is straightforward to calculate, right? This thing we have, right, from this problem. So this thing we have, and we can directly use it. So u is, I mean, let me just directly differentiate it. So differentiating the internal energy, you will get something like this. And then you can combine things to get this, or more simply you can write, okay. So yeah, I think this is, oh, there is T missing in the option. Yeah, it should be T. Okay. This is simple, right? You just have to differentiate this internal energy that we got. Now, since this internal energy is, does not depend linearly on the temperature, it depends as 3 by 2 power of temperature. So that's why the specific heat is also dependent on temperature. Otherwise, it would have been just constant. So this is one thing to notice. So I mean, because you see, this is just, I mean, the specific heat just the derivative of internal energy. So if internal energy is, I mean, behaving weirdly, then this specific heat will also behave something somewhat weird. But if it would have been linear, the internal energy, then specific heat would have been constant, which makes sense. Okay, so any question up until here? If not, let's go to the next problem. So this is a very simple problem. So suppose two identical bodies made of the same material are brought in contact with each other, and their initial temperature was T1 and T2, and then heat transferred from the hotter object and it is completely absorbed by the colder object. Okay, then the final temperature of the system is given by what? So you have one object T1, other is at T2, and these two are made in contact, and then the heat transferred from one to another. Okay, and they are made up of same material. So naively you will think that the final temperature will be just T1 plus T2, right? But that is not the case. Why? Can anyone tell? Yeah? Sorry, and the internal energy is the same that we found before. So the internal energy is, you know, some constant to the power 3 by 2 for this also. So now can anyone tell me why this is not true? Why just the temperature is not just the sum of the two temperatures? Because of this relation, right? Because internal energy depend on temperature as 3 power of 3 by 2. So now if you want to find the so the final temperature, so you, but this always holds, right, for this system. So final internal energy will be just, you know, twice of whatever the final temperature of the body is, like this, right? And which will also sorry, is my voice not audible to everyone? Hello, am I audible clearly, or is my voice breaking?
Yes, sir, audible, sir.
Okay,
Yes, sir, you're audible.
someone wrote me, maybe try increasing your volume, Jyoti. I think my audio is fine. Okay, yeah, so so what I was saying is that, so the final internal energy uh, will be just the twice of the internal energy. Sorry, someone is, okay, someone is not muted. Someone is speaking. Please unmute only when you have to ask something, okay? Otherwise, it creates disturbance. Yeah. Someone raised his hand. Rakesh, do you want to ask something? Okay. Yeah. Now, so what I was saying is that, okay, let me do this again. I think there was some disturbance. Yeah. So what I was saying is that the final temperature is not just the sum of the two temperatures, simply because the internal energy varies like this. Okay, it's not a linear relation. So the final internal energy, okay, of the whole system uh, will be just, twice of whatever the final temperature is there, because uh, as I mentioned, the internal energy is a extensive quantity, right? It add up, like it has the additive nature. So if two identical bodies combine, it will be just twice. Okay, so this is fine. Now also, this internal energy should be equal to, I mean, the internal energy should be, final should be equal to the initial internal energy, right? For the whole system, because heat has been transferred internally, not to external environment. Okay, so this should also hold. And what is the initial internal energy for these two systems? We have kT1 plus kT2, right? And so when you equate these two, so the final temperature will be, so K will cancel from all sides. This, right? Everyone is okay with this? So this does not hold here. This could have held only if this internal energy would have been linear with respect to temperature. Okay, so if everyone is fine with this, let's go to the next problem. Okay, here the internal energy is given again. So now it is written as E, but it is same as U. Don't get confused. S is the entropy, V is the volume, and N is the number of particles, and B is a constant. Okay, and we want to calculate the temperature of this system. Now last time we had given S and we calculated U. This time U is given and we have to calculate temperature. But this is very simple, right? We did it many times. So we know from first law of thermodynamics, temperature is simply this, right? So this is just again to remind you. Yeah, it's a simple problem. I think I should have not kept it. Yeah, this is trivial. This is just the internal energy, it's nothing. Okay, so yeah, this is fine. So let's go to the next one. Okay, so now this is a problem based on a concept. So let delta W be the work done in a quasi-static reversible thermodynamic process. Which of the following statement is true about delta W? Okay, so remember this, quasi-static reversible thermodynamic process. Okay, now the options are: delta W is perfect differential. Perfect differential means exact differential if the process is isothermal. Okay, delta W is a perfect differential if the process is adiabatic. It is always perfect differential, it cannot be perfect differential. So what do you guys think? Can all of you answer it? Like, you can write in the chat, what do you think? A, B, C, D. Guys? So, you know what perfect differential means, right? So, perfect differential means, suppose you have a function f, then the finite change in this, we can write it like this. So, f is suppose function of xy, right? And if del a by del y is equal to del b by del x, then we say that uh, f is a, or df is a perfect or exact differential. Okay, and due to that it is path independent. So if you take your system in any arbitrary path, as long as the endpoints are, same, I mean, as only the change is only will depend on the endpoints, not on the path. So someone, Aditya, wrote B, perfect differential if the process is adiabatic. uh, hmm, okay. So adiabatic means there is no heat transfer. Okay, someone else? Anyone else? So what does this quasi-static reversible means? Can anyone explain?
Sir, a quasi-static reversible process is a
Yep.
process which takes place very slowly and it remains very close to the equilibrium condition.
Yeah. Yeah, that is, mostly correct. So then think about it. So if this quantity is being varied in such a way that it remains closer to equilibrium, right? Then does it matter which path you take? Shouldn't only the end point should matter, like where you reach after this process, right? So suppose in this some this PV diagram, you are somewhere here and you went like this here, uh, B, okay, and this path that you took, it was a reversible, quasi-static reversible, right? And so, and then you took another path similar, anything, you can take any path, right? This is path 1, 2, and both paths are quasi-static reversible, but you reach this B point only. So during the whole path you remained, you remain, closer to the equilibrium, right? And so, whatever path you take, as long as you follow this procedure of having this, quasi-static reversible process, then your path, the path taken will not matter, and so you have, it will be path independent. and we know that path independent changes gives you the exact or perfect differential. So that's why the delta W will be a perfect differential always. It doesn't matter if it is adiabatic or isothermal. I mean, work can be done using the internal energy also. But if the work done is very spontaneous, like some kind of blast, then because it matters how, I mean, then it will be path dependent basically. Okay, so it should be always quasi static reversible in order to remain path independent. So C is the correct option. Okay, so remember this thing. uh, if this is true, then you have path independent processes, and path independent process gives you exact finite differentials. So yeah, okay, let's go to the next problem then. Anyone has any question here? You guys are not participating, I mean, so many people, but not all of you are participating in the discussion. Please try to, so I'll suggest from next on, please go through the lectures on the NPTEL, and then let's try to discuss whatever you don't understand there, you can discuss here. Okay, so let's go to the next problem. Yeah. Someone asked, if sir, if path is reverse, yeah, so so then it will be same amount of work, right? What then the isothermal process? No, I mean, it doesn't matter if you go from A to B or B to A, it will always be path independent, that as long as you are following this quasi static reversible process. Okay, Priyanshu, do you have okay, you are saying keeping the temperature constant? No, even if temperature varies, doesn't matter. I mean, so you are doing work, right? So work is being done, or by the system, or work is being done on the system. So that may change the temperature, but I'm saying this change in work done. Okay, this will be always path independent. Okay, and temperature is also temperature is also a state function, so it will not, it doesn't matter what path you take, as long you reach from A to B or B to A. Okay, so I hope you understand. Okay, if there are no further questions, let's move to the next problem. Okay, so yeah, this is again a problem on paths. So suppose there is a gas which is taken from A to C, okay, reversibly, okay, uh, by two paths. So one is A to C directly, and then one is A to B to C, as shown in figure. Now during the process A to C, the work done is 100 joule. Okay, so just let it write, let us write dW, change, I mean, work done. Okay, and the heat absorbed is 150 joule. Okay, dq. So this is always inexact, the heat absorbed. And yeah, and during the process A to B to C, the work done is 30 joule, and we have to find the heat absorbed. Now you will ask, so why this? I mean, why the work done in both the cases is different if you are reaching from A to C, right? So it is only that it is only a reversible process, not quasi-static. If here quasi-static was there, then these two work done should have been same. Okay. Now, so okay, let's we have to find this. So how do you do this? So I just yeah. Anyone has any idea how to find this? Anyone? Okay, let me. So this is again a problem of sorry. First law of thermodynamics, which tells us that heat. We can find it separating. Yeah, I mean. So yeah, you're right, but so this is the first law of thermodynamics. Now, because we know that internal energy is always a state function, right? It only depends on the point in the PV diagram where you are, not what path you took. Okay, so this du will be same for both these and these paths. Okay, so this will be same. The change in internal energy will be always will be same. Okay, so for A and C, let's write out the first law of thermodynamics. So it is dq is equal to du minus dw, and so we can find the change in internal energy as sorry oh sorry, this is plus change in heat is change in internal energy and work done. Yeah, sorry, yeah. And then du is dq minus dw, which is 150 minus 100, so 50 joule. And this change in internal energy will be same for the process ABC, and so we can write for ABC the heat change, I mean the heat required I mean heat absorbed was du plus dw, that is 50 plus 30, 80 joule, right? So it was just a simple problem to just note that since internal energy is a state function, that's why we can use the same change in internal energy in both the processes, since the starting point and end point is same. Okay, yeah, this is a simple one. Let's go to the next problem. Yeah, this is also a simple problem from high school physics, but there is an interesting thing here. So you have 10 gram of ice at 0 degrees Celsius, and it is added to a beaker containing 30 gram of water at 25 degrees Celsius. What is the final temperature of the system when it comes to thermal equilibrium? Okay, so the specific heat is given, latent heat is given, right? So we know how to solve this kind of problems. So first we can what we do is we calculate whatever, I mean so whatever heat sorry yeah, latent heat is given, right? and yeah, 10 grams of ice. Yeah, so then we can first we need to calculate what how much you know heat required to melt 10 gram of ice, so which is given just mass times the latent heat. Sorry, let me write it first. So it's 10 into 80, so 800 calories required to melt this 10 gram of ice. Okay, and now this is required heat, and what is available. So what is available is the 30 gram 30 gram of water at 25 degrees Celsius, and which is given as m mass times specific heat times temperature. So this is 30 into 1 into 25 degrees Celsius, because you notice the specific heat is given in terms of degrees Celsius, so that's why we don't need to convert it into Kelvin or anything, and we get 750 calories. Now you see, this is 50 calorie more than what we have. So now okay, so now tell me what will happen in this scenario. Anyone has any idea? This is a simple thing, right? You must know at least this. You need this much energy to melt the ice that you are putting inside the beaker, but what you have is this energy, 750 calorie. You are 50 calories short. What will happen? Can anyone answer? Which option is true out of these? Anyone? Hello guys. This is easy, right? Think about it. Hello? No one wants to answer? It's okay. I mean, you can be wrong, but you should try. A. Why? Swastik. Why do you think 0 degrees Celsius at equilibrium? You are right. But why? Simple, right? I mean, so whatever heat that you have available is not enough to melt the ice, so it will just required energy is not sufficient. Yeah, that is fine. Yeah, so it will be just used up by the ice. Okay, but you know that melting is a phase transition. Okay, it will only melt, I mean even if you supply 800 calories, that will also lead to same answer, 0 degrees Celsius. You need 801 calorie to raise the temperature of the system. Okay, just melting is not enough. So yeah, I mean, this is correct. Okay, so let's say a conceptual question. I mean, it's from high school. So let's go to the next problem. This is also a simple problem. So this is the last problem of today's session. There is a vessel So everyone should try to solve this. So this is very simple. It has two compartments, V1 and V2 volume. They may not be the same, and both of them contain ideal gases at pressure P1 and P2 and temperature T1 and T2. Okay. Now if this wall is removed, so if we remove this wall, okay, what will happen? What will be the resulting equilibrium temperature? T. So now we had this kind of problem earlier, right, where we had two identical blocks made contact with each other, but there we had the relation of we knew the internal energy as a function of temperature and all, but here we don't know what is the how the internal energy behaves with temperature. We just know that this is an ideal gas, and for ideal gas we know the equation of state, right, which is n PV is equal to n kBT, where kB is the Boltzmann constant. So we know this. So see, so this is what constrain this whole thing. So the temperature depends on basically pressure and volume. Okay, these three quantities are not independent; they depend on each other, right? And we know that volume is extensive quantity, so final volume will always be V1 by plus V2. Okay, number of particles is extensive quantity, so n is equal to n1 plus n2. That is also true, right? And from here, and for both the systems you can write this equation, right? N1 kT kBT and P2 V2 is equal to N2. Kb is constant, the Boltzmann constant is obviously constant, right? And so from here you can write right? And also one more thing is there. You know that internal energy is also extensive quantity, so total internal energy or the final internal energy will be just the U1 plus U2. And for ideal gas we know that the internal energy is given by this thing, right? So U final is just N1 CV, and because the both are same ideal gas, so CV will be constant, common. Okay, and from here what you get is, and let's say the final temperature is, so NF CV TF is equal to, so CV cancels out from both sides, and you are left with NF TF is equal to N1 T1 plus N2 T2, right? And so the final temperature, and then and you have NF from here, right? And N1 T1 N2 T2 you can replace from here and here, so this will be just N1 T1 will be P1 V1 by Kb plus P2 V2 by Kb divided by NF, and NF is just N1 plus N2, which is P1 V1 Kb T1 plus P2 V2 Kb T2, right? Kb cancels out, numerator and denominator, and you are left with P1 V1 by plus P2 V2 divided by P1 V1 by T1 plus P2 V2 by T2. Okay, so this is the final answer. So yeah, again it is very it is not that straightforward that you have just T1 plus T2, because the pressure is different, volume is different, and this equation of state governs how your temperature depends on pressure and volume. So yeah, so that's why this complicated formula for final temperature comes up. Okay, so yeah, just to remind you that nature does not behave simply. It has some laws and some constraint that it has to follow, and so that's why uh, the answer is not always very simple. Okay, so yeah, this is the last problem for today's session. So anyone has anything to ask, any question, any doubt, or any general thing that you want to discuss, since we have time? Or everyone want to enjoy their weekend? Okay, so I think no one has anything to discuss. So yeah, let's end today's session. Thank you for joining. Yeah, I'll request you to go through the lectures on NPTEL, and if you don't understand anything, ask me. I will try to explain that. And so I'm also so as I told you, my research does not deals directly with statistical mechanics, so I'm not also very expert on this subject, but yeah, we can have a discussion. We can try to figure out something together. Okay, so yeah, thank you for joining. Unless you have anything to ask, you can leave, and let's meet next Saturday, 6 p.m. Okay. Okay, so yeah, thank you, bye.
Thank you, sir.